myself, just to see if you've got a conceptual understanding of this section. So there's only like 1 or 2 actual calculation problems. The rest of it is just conceptual questions. They're pretty straightforward.
That sounds great.
Yesterday we went over when can sampling distribution be used. I gave an example of you ask every 5th student who enters Western High School about their belief in ghosts. 90% of them believe. You stopped asking, can you conduct a sampling distribution? Can you consider this being an accurate survey? Independence and randomization is met by the fact that you ask every 5th student. We did not ask them what the 10% of the population by asking 50 people. And then we talked about you need at least 10 successes and failures. 90% of 50 is 45 believes. There's only 5 that do not. So we do not meet that condition. We don't meet condition 4. So you would need to rethink your study. Now, what we're going to get into today is more so of the math behind it. These are all concepts. But now I want to get into strictly binomial distribution. Did we learn this lecture? We learned about binomials, but not binomial distribution.
Sorry. A whole new concept? Whole new concept to cry over for hours upon hours?
A binomial distribution is, well, what's the root? What's bi?
2.
2. So it's a sample that includes 2 outcomes. Typically, success and failure. A sample that includes 2 outcomes, typically success and failure. We've been talking about it. If you go into a store and you ask people, I don't know, anyone can think of something you ask people?
How many times have you cleaned out your shower last night?
It's got to be success, failure.
Do
Do you clean your shower on a weekly basis? There we go.
There we go.
Yes, no, right? Success, failure. If you go ask 50 people that, and you're to draw a histogram of that data, it's going to be a binomial distribution because if you're to draw a histogram of it, you're going to have the yes, you're going to have the no. Does that make sense to everybody? So binomial distribution, if you just go out and collect one sample, isn't enough to do normal distribution. But if you were to do repeated collections, and you were to look at the percent or the proportion of yeses, and you were to do that at least how many times? Do you remember? 30 times. Looking at those 30 individual proportions can be looked at, and then that you can look at binomial distribution in a manner where you can treat it as normal distribution. Does that make sense to everybody? Okay, so binomial distribution is, of course, dealing with categorical data. Success, failure, 2 groups. Okay. Looking at the proportions, of multiple samples, greater than 30, greater than or equal to 30, allows us to analyze this as a normal model. That does not make each sample normal. Each sample is still a binomial distribution. It's either a yes or no. It's got 2 bars in its histogram. 2 bars cannot make a bell-shaped curve. Okay? But if we look at a bunch of samples of the same kind of survey, look at a bunch of them, the proportions all combined can be looked at in terms of a normal model. So that's a big thing to make note of and remember from this section. Okay, so now if we can do that, then we can treat it like normal distribution, which means now we can look at binomial distribution through the concept of z-scores. Okay, so we have binomial distribution Let's go back and recall what the z-score formula is. It's z equals what? X minus
X bar.
x bar over
Standard deviation.
standard deviation. X represents the what?
Your outcome. I mean, yeah.
All your eggs.
X represents the raw data, right?
Yeah.
Like your raw test score. It's the data that you're looking at. X bar represents the mean, the average. And then the standard deviation is the standard deviation of your
X variables.
standard deviation of your x variables, which is your data, right? So we're taking a look at some data point, we're subtracting the average, which is what should occur, and we're dividing it by the standard deviation of our data. Okay? So now we're going to convert this same concept into binomial distribution. If we collect a sample, we're going to have a sample proportion, right? Our sample is going to have a proportion of yes or no. Our sample proportion theoretically should be the same as the what?
Sample.
The population proportion, right? If 40% of the United States is Democrat, theoretically, if we were to go select 100 people, we should get 40 of those people are Democrat, theoretically. So what we should get is the population, but will we always get the population?
No.
No. It'll be affected by the standard deviation, which is based on our sample size. Okay? So our formula for z-score in terms of binomial distribution, our mean is what we should get. Mean, the average, is what should happen. If the class average is 70, then if I ask some random student, then theoretically they should get 70. So the mean in this case is going to be our population proportion. But if we go out and collect a sample, what our sample results in is not necessarily going to be the same thing. So our data in this case is going to be what we collect, which is p hat, the sample proportion. And then we divide that by the standard deviation of our data, which is the standard deviation of p hat. Because p hat, what we collected, our individual proportion is, our individual sample proportion is our data.
Wait, Jim. If y hat is the predicted, then if p
That's linear regression. That does not deal with the normal model.
hat. Okay.
Okay. We're talking about p hat. P hat is it's going to be later be used as a prediction, but p hat represents what we get in a sample. Whereas y hat represents a linear regression model. That doesn't necessarily have to do exactly with the normal model. Okay. So what that means for our normal model is our normal model, in terms of we've done several repeated binomial distributions. We've collected them. We put all of the proportions of those put together. We made a normal model. Theoretically, what should be in the middle is our population proportion. Will our sample proportion always match our population? No, it has some fluctuation. We have these lines in the sand. These are our standard deviations. Standard deviations below, standard deviations above. This represents how many standard deviations above?
1.
1. This represents 2. Okay? Let's remember, a standard deviation of p hat. Remember what the formula was? We heard that yesterday.
Oh. Square root of p multiplied by q divided by n.
P over q divided by n. Okay, so we've got enough information to look at this as a normal model. And within 2 standard deviations, according to the empirical rule, comprises how much of our data?
95.
This represents 95% of our data. Right? This line in the sand the way you calculate it is you do the P, the middle, plus how many standard deviations? 2 standard deviations of P hat. And this line of sand down here is P minus 2 standard deviations of P hat. Yesterday we went over a 95% confidence interval. What was the bottom end of it? P minus 2 standard deviations, and what was the top end of it? P plus 2 standard deviations. Does that make sense, everybody?
Yeah.
How this all ties into the empirical rule. Okay, this is 94% of our data. This is where the formula for our 95% confidence interval comes from. Okay, does that make sense? Okay. So, this gives us a technique to predict accuracy. Here's an example. The CDC, that's the Center for Disease Control. Okay, the Center for Disease Control reports that 22% of 18-year-old women in the U.S. have a BMI, body mass index, of 25 or more. The CDC, the Center for Disease Control, they are a nationally funded organization. In terms of whatever they release, that's considered being the population. Okay, so when they say 22%, they're a company that's been hired. They're a company that's done enough surveys that they have a large enough data set that they kind of own the market on reporting the population. Does that make sense to everybody? They've asked enough people that they can be considered the population. Now, a college, this college is not testing if the CDC is correct, but the college is going to say, okay, let's use what the CDC is reporting to test something. So the college wants to test the accuracy of self-reporting. Self-reporting means rather than actually having a doctor come in and measure the 18-year-old's BMI, they just say, there's usually a formula for BMI that involves your height and your weight. So they say, what's your height, what's your weight? And then from that, they can calculate the girl's BMI. They're testing the accuracy of self-reporting. Does it seem like, given the opportunity to report their weight, are they giving an accurate measurement? Or does it seem like the girls of interest are reporting either light or heavy? Okay? So they asked 200 college freshmen
Does it matter if they're self-conscious about their weight?
when you pick them randomly, you don't know if they are or not.
Nah.
They asked 200 college freshman girls their BMI. 31 report a BMI of more than 25. Does self-reporting, or sorry, is self-reporting an accurate way to collect data? Is self-reporting an accurate way to collect data? So, okay. Here's where we can go from this. First off, we want to identify what is the population proportion. What's P? Anybody? Population proportion.
Oh,
Population proportion.
United States.
22%.
Is it?
22%.
22%. The CDC, that's exactly what I said at the very beginning of this problem. The CDC is a large enough organization that whatever they say is the report is accepted as being the population. So the population proportion, the CDC is reporting at 22%. So the population proportion we're going to use is 0.22. What is our sample proportion?
31.
31 over 200. 31 out of 200 have committed a success. They've reported a BMI of more than 25.
That's not particularly good, is it?
That's 0.155. So just looking at the P hat compared to the P, without taking into consideration standard deviation, is it lower or higher?
Lower.
It's lower, which means that they're reporting lower. But then the question arises, is it too much lower? Okay? Because, yeah, it's, what, 6.5% off of being what it should be. But if the standard deviation is 10, then that's not that far away from it. But if the standard deviation is 2%, it's almost 3 standard deviations away. It's over 3 standard deviations away. So before we can compare how far this is from that, we need to figure out what is our standard deviation of our data. The standard deviation of our data is dependent upon our sample size. The formula is the square root of what goes on top. P, which is 0.22, times Q, which is
0.88.
not 0.88,
0.78.
0.78. You had the right idea. Divided by the sample size. The size, however many people you ask will affect your standard deviation. How many people did they ask? They asked 200 people. So based on asking 200 people, they have a standard deviation of 0.029. Punch that in, you should get 0.029. Now, in terms of self-reporting, there's 2 ways we can do that. One, we can construct a 95% confidence interval. Or 2, we can calculate a z-score. It does not matter how we do it. Either way works. If we were to conduct a 95% confidence interval, the formula is you take the population and you minus 2 standard deviations, and you take the population and you add 2 standard deviations.
It's more than 3 away.
Anybody have?
Can you make standard deviation lowercase?
Yes. So
Okay,
then like
because it looks like
25
25.
Yes.
Yeah.
Yes. I see what you mean. Yes, I can do that.
It looks like
250. Yeah, I can see that. Yeah.
Thank
Okay. Okay. So define the 95% confidence interval. We're going to do 0.22, take away 2 0.029s, and then we're going to take 22% and we're going to add 2 0.29s. So we get anybody have this?
With your minus unit, it's 0.162.
0.162, and then if you're adding it, you're going to get 0.278.
They recorded like
I didn't-
I think. I don't know. That's not how you're right. 2 times 2.9% is 5.8%.
Minus part.
Oh.
And then add that to 22%. Yeah, 27.8%. Yeah, 0.278. Okay. So remember, 95% confidence intervals means that 95% of the time, if you collect a sample that is of the size of 200, your answer should be somewhere in between these two values. That's what a confidence interval tells you. Okay, so maybe that would be good to write this down. 95%. 95% of the time, a sample of 200 will have a sample proportion, p hat, between 16.2% and 27.8%. So 95% of the time, if you collect a sample of 200 people, if self-reporting is an accurate model, you should get an answer of somewhere between 16.2 and 27.8%. This college got a reporting measurement of what? Is it inside of this confidence interval?
No.
No. So that means that the chance of that happening is less than what?
5%. 2.5.
2.5%. Because it's on the bottom tail, right? And this is the 95% confidence interval. That means these two tails combined make 5%, making this bottom tail worth 2.5%. So the chance of doing a study accurately, completely accurately, and getting accurate results and falling outside of this interval on one side or the other is only 2.5% chance. So most likely self-reporting is not an accurate model. Shannon, does that make sense?
Yeah.
You sure?
Yeah.
Okay. All right. So is self-reporting an accurate way to collect data? We can't say for sure, but we can say it does not appear. It does not appear self-reporting to be is an accurate model, accurate way to collect data.
Do people who don't go to the school subscribe to your videos?
I guess they could. I don't know. It does not appear self-reporting is an accurate way to collect data. That's one way of knowing this answer. There are several ways to find the same exact answer. We're going to do another way momentarily. Another way is through the use of z-scores. Okay, we're going to do the same problem now with z-scores. The formula for z is we take what we got, we subtract what we should get, and we divide by the standard deviation of what we got. And it's what it always is. It's always data minus mean over standard deviation of data. What we got minus what we should have got divided by the standard deviation of what we have. The college collected 0.155. According to the CTC, they should have gotten 0.22. Divided by the standard deviation, which was 0.029. Does anyone have that? I think it's negative 2.
Negative 7.
Negative 7.43.
This is why everyone needs to make sure they got their calculator out.
Negative 7.47.
Negative 7.4.
I got negative 2.24.
Negative 2.24. You have to make sure the top is in parentheses if you're typing in all at once. Okay, that's the reason it's important to make sure everyone has their calculator out getting these answers. Because it is, if you type it in wrong, you will get the wrong answer. So we get negative 2.24. Well, if we think about this, We don't need actually need to make a confidence interval. What's the z-score in the middle of a graph?
0.
0. The 95% confidence interval goes from -2 up to +2. This is where 95% of the data, 95% of the time, we should get an answer between -2 and 2. So rather than making a confidence interval, we would just look at the z-score. Where does the z-score fall?
Outside of the -2 area.
It falls down here at -2.24. It's outside of the reasonable realm of possibilities. Does that make sense to everybody? And the reason is because the absolute value of -2.24 is greater than 2. Means it falls outside of that 95% confidence interval. If you were to sketch it as a picture, it falls outside of the shaded region of possibility. Is there any questions on that?
So if your number was positive 2.24, would that mean that there's only, same thing, that there's only 2.5% chance?
Yeah, because it's 2.5% above. There's only 2.5% chance that what your data is higher than what.
Okay.
Because these two combined make 5%. So, now here's something else we can do. What is the probability of this being an accurate study, but still occurring? What is the probability? What letter does the word probability start with?
P.
What word does proportion start with?
P.
What word does percent start with?
P.
Word, not word.
Oh,
What letter? P.
You got it.
All right, we're going to use a p-value to get this answer. Does that make sense, everybody? What is the probability of this being an accurate study but still occurring? We need to find the p-value for this z-score because that's going to tell us the actual area of that region. Okay, we said there's approximately a 2.5% chance that this could actually occur, right?
Yeah.
We said approximately 2.5% chance this could occur.
It's on 0.0120%.
Okay, if we look at the p-value for a z-score equaling -2.24, Hannah, go ahead.
I saw 0.0122, so it's like 1.22%.
So the probability of this actually occurring is 0.0122, or you can say there's a 1.22% chance that this is an accurate study. Does that make sense to everybody? That's how slim of an odds this would be, that self-reporting actually is a accurate way, but this study just happened to give false data. There's only 1.22% chance. Now, Tyler, your question was, what about positive 2.24? If you were to look at positive 2.24, would you still do area to the left?
No.
No, because if you want to know what's the chances of being up here, you want to find the area to the right of it. Otherwise, you'll get like that. There's like a 98.9% chance that it's still successful. So no, you want to say what's the chances that we're up here in this top sliver? So you find a p-value to the right.
All right.
Hello. Sure. Tyler, the office needs an extra class. Okay. So, Tyler Fowler. Did I say Tyler? Sorry. Tyler Fowler. The office needs an extra class. All right. This example should take you to enough information to figure out the homework. Suppose 13% of the population is left-handed. I do not remember where I found this information at. Okay. I cannot remember. Suppose 13% of the population is left-handed. So it's telling you, assume this is true. A 200-seat auditorium has 15 lefty seats. Some of the seats in the round room, I believe, are left-handed seats.
The ones on the left side.
Is it all of them?
Yeah,
But like all
all
of
the
them,
left-handed end seats.
yeah, they're all broken though. Like all of the seats are literally broken. They're all like down at that 45 degree. It's like like instead of 90 degrees, like sitting down 90 degrees, it's like down to like one side down.
In a class of 90, what is the probability? Which means we're going to need a what? P-value. What's the probability that there are not enough seats?
Wait, before you read this, you said homework, right?
Just takes you up to enough information to do the entire assignment. Yes. Suppose 13% of the population is left-handed. A 200-seat auditorium has 15 lefty seats, seats that are designated specifically for people that are left-handed. In a class of 90 students, so 90 students are going to walk in, they're going to try to find a seat. What's the probability that there are not enough seats? Okay, when there's 90 students that walk in, we don't know how many are left-handed. Right? It could vary. There technically could be 0 left-handed students, but there could also be 90 left-handed students.
They're all left.
It's unlikely that there's going to be all left-handed. Very unlikely, but it could happen. It wants to know what's the probability that there are enough seats. So what we're going to do is we're going to find, in order to find a probability, we need a p-value. In order to find a p-value, we need a z-score. So we need to find a z-score. The z-score formula is dependent upon knowing your population, your sample, and the standard deviation of your sample.
The other way around.
Did I write it back or I did? I had a professor. He made a mistake. Did I tell you this story? Yeah. This is my same professor. I'm going to take a midterm for tomorrow. And he made a huge mistake in a problem. We got halfway through it. And one of the students is like, Dr. Whittaker, shouldn't that have been an A instead of a C? And he's like, yeah. And so he like runs over and he erases it and he fixes it. He turns around and he goes, you know the best part about being a professor? And of course, the girl's like, what? He's like, if I make a mistake, we erase. If you make a mistake, I take points. And he just went back to teaching. But he thought that was the funniest thing. So, if I make a mistake with the hats, we fix it. If you make a mistake, you cost points. Actually, it costs all the questions. Okay. The z-score. P hat minus p. First off, what is p?
P is 0.13.
0.13. Okay, it's telling us that suppose 13% is left-handed. We're told to assume that. Our population is, or our sample proportion, is what's going to happen in our case.
X. You don't know. You don't know how to know.
What can be our, at most,
15
students left-handed, right? Out of
200.
90. Because there's 200 seats. So that 200 is irrelevant. Because if there's a 90-seat auditorium, 110 of them will just sit empty, right? So the main thing is we need to find out what's the chances that our sample proportion is going to be 15 out of 90 or more. So we do 15 out of 90. What is that? Anybody?
1.6.
0.166 repeating, right? Okay, so we'll leave it like this. And then our standard deviation of our sample is the square root of 0.13 times 0.87 divided by 90. That's 0.035. If there's a 13% chance of success, there's a 87% chance of failure. Remember, it's always P times Q. It's always P times Q, success and failure. If there's a 13% chance of success, there's 87. You always subtract this by 1, from 1. Okay, right? All right, so we get 0.035, and then now we fill in our z-score formula. 0.166 minus 0.13 over 0.035. That takes us to a z-score of 1.029. If we were to graph this on the normal distribution model, we were to graph this, 1.029 would be somewhere in here, correct?
Yeah.
If there's fewer than 15 people, is that okay?
Yeah.
Yes. The only dilemma is if our class has
More.
more. So is that to the left or to the right? More than 15 would be all of the values to the right of 1.029. So we need to find the area of this region. Our p-values do not give you the area to the right, they only give you the areas to the
Left.
left. This is the same as the area to the left of negative 1.029. The area to the right of positive 1.029 is the same as the area to the left of negative 1.029. What is the p-value for the z-score negative 1.029?
0.1539.
0.1539. Everyone agree?
Yes.
All right, so going back to the original question, we've got 1.029 is the z-score. The amount of area above is 0.1539, so the probability that there are more than 15 students in a class of 90 is 15.39%. The probability that there are greater than 15 left-handed students. Now, it's not just greater than 15 left-handed students. It's greater than 15 left-handed students in a class of 90. Because if I was to knock the class size down, if I was to say, okay, the class has only got 15 people in it, is the chances of there being more than 15 left-handed students the same as if there's 90 people in the class? No, if there's only 15 students, the chances of there being more than 15 of them left-handed is 0. So it's all dependent upon the class size. So the chances that there's more than 15 left-handed students in the class of 90 is 15.39%.